The mean value theorem, MVT. The mean value theorem for differentiation states that if f is continuous on a closed interval a, b and differentiable on an open interval a, b, then there exists a number x equals c between a and b such that f prime of c equals f of b minus f of a over b minus a. The slope of the tangent line on the left-hand side equals the slope of the secant line on the right. Alternatively, this is written as f of b minus f of a equals f prime of c times b minus a. The mean value theorem for integrals states that if f is continuous on a closed interval a, b, then there exists a number c between a and b such that f of c equals 1 over b minus a times the integral of a to b f of x dx. Graphically, if f is above the x-axis, then the integral from a to b f of x dx represents the area below the curve above the x-axis from a to b. What the mean value theorem implies is that we can find a number c such that f of c is the average height of the function, and so f of c times b minus a is the area of the rectangle, which will give us the area under the curve above the x-axis from a to b. Example: show that if f is continuous on the closed interval a, b, where a is not the same as b, and if the definite integral from a to b of f of x dx equal to 0, then f of x equals 0 for at least once in the closed interval. Since the function is continuous on the closed interval, by the mean value theorem for integral, there exists a number c such that f of c equals 1 over b minus a times the integral from a to b f of x dx. But since the definite integral is given 0, then f of c equals 1 over b minus a times the integral implies that this is 1 over b minus a times 0. 1 over b minus a times 0 is 0. And so f of x is 0 as x equals c. F of c is 0.